Hi, everyone, and welcome to the second session of the Challenging Climate Change sessions. Let's see, for questions and answers during this session, if you look over to the right, you can see that there is a general chat and also a Q&A section. If you can write your questions in that section, our speakers will get to the Q&A at the end of their presentation. Let's see, to start, I'll share my screen here. We'll go through what we need to do. Oops. Sorry, bear with me for a second here. There we go. Okay, so thanks for joining us for this session. And the session today is how buildings can reverse climate change. We did this through their presentation. To start the session, we would like to take a moment to honor the land and thank its original stewards. In the Seattle area, we are on the ancestral lands of the Duwamish and the Salish Sea tribes. If you're attending from another area, we encourage you to learn on whose traditional lands you work and live. We want to remind everyone to exercise respect for other attendees. Please help us foster an inclusive environment during our sessions. If you are someone that normally speaks first, please check yourself and leave space for those, particularly BIPOC colleagues, who may have been socialized to hold back. And if you normally hold back, consider taking up space here. We'd like to take a quick moment to thank our sponsors, especially presenting sponsors, which include Dunn Lumber, Small Planet Supply, and Tacoma Public Utilities, and our sustaining sponsors, King County Green Tools and Farrow's Creative. This event is truly not possible with the support of all of our sponsors, and we are truly grateful for their support. Okay, and stop sharing for a second here. There we go. And at this point, I will invite Chris Magwood to go ahead and turn on his mic and camera and begin his presentation.
Yeah, thanks everybody. I'm just looking around to make sure I can see my slides. Okay, there we go. Yes, I would very much like to thank the organizers for inviting me to present today. And I must say, I sure wish I was live out there with you all in the West Coast. It would be a great way to actually meet everybody. And the organization is one that I have sort of been aware of and subscribed to for a long time, but have never actually been to one of your events. So I'm glad to be here, but I would much rather be with you in person. But I hope we can still have a good conversation anyway. I'm going to present a fairly short slide deck, and then Lucas will follow me as well, and then we're going to leave quite a good period of time for a Q&A session at the end. So yeah, you can just sort of type your questions into the Q&A section. I can't sort of see them as we go, but we'll make sure that we leave lots of time at the end for this. And I guess by way of introduction to myself, my name again is Chris Magwood. I work at the Endeavour Centre, which is a not-for-profit sustainable building school in Peterborough, Ontario, Canada. And over the last 2 years, my colleagues at Endeavour have been very generous in letting me kind of start a sub-organization here called Builders for Climate Action, where I've been working on thinking a lot about how buildings can not only impact the climate less, but also potentially be a climate change solution in terms of drawing down and storing carbon. And so that will be the kind of overall focus of my talk, although I'm going to sort of start a little wider than that and narrow down. But I'm really excited to be in the company of colleagues who have likely been thinking about these things and acting on them for some time, and looking forward to the discussion. So this is a particularly relevant question for an eco-builders guild, but the question comes up in our practice all the time. What do we mean by this? We call our school a sustainable building school. People use eco, people use green, people use regenerative. There's a whole bunch of language that can sort of, in an overarching way, describe what we do. But it is really important, I think, for us all to be thinking about what specifically is it that makes us eco builders or green builders or sustainable builders, or whatever kind of word we want to use to describe ourselves. And over my 25 years of working with clients and building officials and manufacturers and all sorts of people in the industry, the sort of answer to what is an eco building is pretty widely scattered, and people mean very different things by that. And so for us in our practice, it's really important to sort of understand what we mean, but also then what our clients mean and what the expectations of others who are going to be involved in the project will be. And those criteria, are fairly widely scattered, and sometimes they overlap. You can make a building where they, all overlap, or you can really just be focusing on one of them. And so that's why I think it's important for us in our practices to really be conscious about what we mean, because the results vary widely depending on what we mean by an eco building. So I just did, before this presentation, a very quick online scan of like, what are the greenest buildings in the world? And there's all kinds of ways to look at that. There's the building on the top left has the best LEED score ever achieved. Shanghai Towers has a LEED Core and Shell Platinum and has the highest rating from China's Green Building Evaluation System. The one on the bottom right has the best BREEAM score, which is sort of a UK and European version of a green building program. The one on the bottom left is actually very close to me, where I live in Ontario, and is a Living Building Challenge certified building. And so, all of these buildings lay claim to being, eco buildings, but they're very different in terms of, what they look like, how they operate, and what the sort of designers and builders and clients meant when they meant green. So, that's sort of the underlying purpose of getting started here, is to just make sure that we're never going to, and I don't think we want to, have complete agreement across the industry as to what we mean, but to at least be very clear in the claims that we're making and what it is we're setting out to do. We built Great Endeavor. The one on the left is an office for the local teachers union. The one on the right is a completely prefab straw bale house that can be taken apart and put together multiple times. You could put your best building there and say this is one of the greenest buildings in the world. So we can all make the claim, but I want to talk a little bit about what we mean when we actually make that claim. So we're all trying to do something better than what is out there, what we see as sort of the mainstream or the industry norms. But if we're doing better, how is it that we go about proving that we're doing better? And are we able to continuously improve, what our version of better is? So in our practice, we work with a basic set of 10 criteria that we sort of explain to our clients and get their feedback on. And these are in no particular order of importance, but ecosystem impacts, embodied carbon, energy efficiency, indoor environment quality, waste, resilience, durability, building code compliance, material costs, and labor issues are all things that we think are sort of central to our version of green building. But depending on our clients' outlook, certain projects may focus more heavily on one of these 10 than others, or a group of them. And so, actually taking the time to define which of these things we're setting out to pursue kind of our first step in doing a project. And then obviously there are always project specific criteria that don't fall into these categories. We've done buildings where somebody said all the materials have to come from within a 200-kilometer radius. That's another criteria that gets added. Having an educational component might be a criteria. There are things that go beyond these 10, but what we found is that these 10 really helped us capture the main elements that people are interested in. And then for us, what that's meant is not just defining that, say, in this case, energy efficiency is something that's important to our clients and our practice, but how are we going to measure that and how are we going to define that? And so we kind of have a sort of 4-tiered system where somebody could tell us, that all they want to do is meet minimum standards. So energy efficiency would not be a key part of a building. They might say that they want to improve it by a specific amount. So we say reduced energy use is sort of 25 to 50% less than code minimum. We offer a sort of low energy range of 50 to 75% less than code, or a very low net zero kind of net positive range where you're getting towards the 100% less than code version. And so within each of those categories, we sometimes rely on existing standards to be able to measure that or verify that. But this is sort of the process that we go through. And we have similar things for a bunch of the criteria. And I'm not going to spend a bunch of time with you. If you're interested in this matrix, it's on our Endeavor Center website, so you can check it out. But we're trying to come up with metrics to measure all of these things. And about, I guess it was close to 10 years ago now, sparked by a question from my own daughter, who was a teenager at that time. She knew I did this green building, eco building thing. She had been obviously on the periphery of it all her life and seeing it and hearing about it. And at one point she asked me very bluntly, Dad, is what you're doing, does it help the climate? She's a kid starting to be worried by what she's hearing about climate change and the kind of conditions she might be facing. And, we're clearly hearing from lots of young people like Autumn Peltier, like Greta Thunberg, and thousands and thousands of others who do the school strikes and other actions, basically asking us, our generation, my generation, your generation, to actually make sure that we're doing something to try to leave them a viable climate, which seems like a decent and reasonable thing to be asking. And so, this is where I took the beginning of my deep dive into looking at the material carbon emissions, or sort of the carbon footprint of building materials. And I tried to start that by just looking at, one of our projects that we had built here at Endeavor and see, so what was the carbon footprint if I look at it for all of our materials? And what I found at that point 10 years ago was that this is really hard to do, but it also seemed that, as somebody identifying as an eco builder, that if I wasn't able to understand the impact on the climate of my buildings, I wasn't really an eco builder. So I had to learn how to get this right. And I wanted to be building buildings from over at the far right hand side of this spectrum, where I could basically say, this is a zero carbon building on the material side, or ideally, a carbon drawdown building that's actually storing more carbon than was emitted. So I knew that's where I wanted to be, but I didn't know how to know if I was getting there. So I actually sent myself back to school. I went and did a master's at Trent University, so I could take a bit of a deep dive into this topic. And what I found was that if I took a model building, so in this case it was a small 10,000 square foot, 4-story multi-unit residential building, if I built that building to our building code here in Ontario with viable materials that would pass code, that all met the same level of minimum energy requirements for our code, that depending on the materials I chose, the carbon footprint of that building could be wildly different. So if I was picking my range of materials from the upper end of the carbon emissions spectrum. So things like high carbon concrete, XPS and closed cell spray foam, et cetera. You can sort of see the list of major components there for that building. That the building could have sort of upwards of 240 kilograms of emissions per square meter of floor area, which is a lot. If you think about this building, being somewhere in the neighborhood of 110, 120 square meters, times that, this building is responsible for tens of tons of emissions. Actually, I think it's about 200 tons of emissions in total. So, there's no way that we can say we're being responsible for the climate if every building we build, has hundreds of tons of emissions associated with it. And then I picked, a range of materials that same building could be built out of that were sort of from the mid-range of carbon footprint that was available. And again, you can sort of scan that list, things like mineral wool, fiber cement cladding, et cetera. And I could get the carbon footprint of that building down to 90 kilograms per square meter. So, less than half of the previous example, but still too high. We don't, in no way do we fix climate change, let alone slow it down, when every building we make still, could have 80, 90 tons of emissions associated with it. So the next model that I built was one where I picked materials that were widely available, fully code compliant, and in relatively common use in the construction industry already. So you can see, it includes things like cellulose and wood fiberboard insulation, high SCM concrete, things like that. And here's where I started getting excited, because what I saw was, that material palette for that building basically made it a zero carbon footprint building. The calculations show it being just slightly on the net storing side at minus 11 kilograms of emissions per square meter. But, that's pretty hovering right around the zero mark. I'm not including mechanical, electrical, or plumbing materials in here, because the data on those is still really scarce and tough to find. But a really great result where you can start to say, oh yeah, that's pretty close to a zero carbon building. And then my final model was, well, what if I sort of picked all the best materials for the climate, regardless of whether they're available here or in common use or code compliant? But I did want to make sure that I was choosing things that either ourselves at Endeavour or other people have used successfully, and have sort of a demonstrated application. So things like an ICF block from Europe that has both waste wood chips and a wood fiber insulation insert, expanded glass insulation under the slab, straw insulation for the walls, things could get that building now to be really heavily on the carbon storing side. That model coming at about 137 kilograms per square meter. So, the takeaway from this for me was materials matter a lot. This is for the end user, and for the energy efficiency side, this is the exact same building. And so, if the same building fulfilling all the same roles can have such a different carbon footprint, then we really have to be conscious of the materials we're using, and trying to pick the things that are the most responsible possible for the climate. So that was based on a model building. So not something that had actually been built. Right now, we're working on a study for the cities of Nelson and Castlegar in British Columbia, where we're working with actual as-built homes in those regions. And here's the sort of spread of results we're seeing from actual buildings in the study. So, at the high end of the result is, over 300 kilograms per square meter. So, there are actually buildings being built that are worse than my worst case scenario. The average across the 34 buildings in that study was 157 kilograms per square meter. So, kind of right in the middle of what I had said in my first study would be the sort of moderate or the best, or the worst, sorry. Slightly disappointingly, the best result in that study was still 91. So, not a very great result. But after we had completed the study, somebody came forward and said, hey, why don't you model this building that I'm working on? And that one turned out to be 2 kilograms. So again, very close to a zero carbon building. So we kind of see the same spectrum range, not as good on the carbon storing side as the study indicated, but in the sort of like average type buildings, about what we expected to see. Now we get all of our information for doing this from documents called environmental product declarations, or EPDs. And this is an ISO standardized way of reporting on building materials and the emissions from producing them, according to sort of an internationally agreed on set of rules that kind of define the parameters, what you count, what you don't count. And what that means is that we get a pretty good comparison within material categories of the carbon footprint of different materials. And they give that to us as something called a global warming potential. And one of the tricky things about working with EPDs is that different types of materials will report their global warming potential in different ways. So somebody might say, my material has 10 kilograms of emission per kilogram of material, and somebody might say mine has 100 kilograms of emissions per cubic meter of material, and somebody might say a square meter of my material has this many emissions. So it can be, there's a lot of math involved in sort of making comparisons, even though the source data is supposed to be comparable. And so for my own purposes, and then now to help other people do this, I helped build a tool called Beam, which is a spreadsheet calculator that sort of allows it. All of that math from the EPDs happens in the background, and the user can just identify the size of their building here on the intro page by area, and then move through different tabs of all the different components of the building and select the materials and be able to see what the carbon footprint of the building that they're proposing would be, and then to be able to make changes to change out different materials or change the design in certain ways to try to make improvements on that. So we took this estimating tool and did a study with the Canadian government. Whoops. And the cover of that study is supposed to be here on the screen in front of you, not this blank. I'm not sure what happened to that illustration, but this was really exciting for us because it allowed us to, first of all, be engaging with the national government. They were interested in starting to look at the carbon footprint of building materials and to put out a report that's starting a lot of really interesting conversations. And what we found, the initial findings aren't going to be surprising to a group of eco-builders. We found that a code-built home that uses natural gas is not particularly energy efficient. So 3.5 tons of emissions per year from heating the building and heating the hot water for the building. Or if we look at a 20-year window, that's 70 tons of emissions. If we make that building more energy efficient, we go up to tier 4 of our national building code. We drop that to 2.7 tons per year, or 54 tons over 20 years. It's an improvement, but we don't fix climate change if our buildings are still emitting that much. So then if we can get rid of burning fossil fuels and move to all electric homes with a pretty clean, our Ontario Canada grid is a fairly clean grid. We're now getting that below 1 ton of emissions per year from the home, just over 14 tons for the 20-year window. So now this is starting to look like maybe we can achieve something on the efficiency side. And if we make this a really well-insulated, airtight, all-electric home, now we're down to under 0.5 ton a year and only 8.8 tons for 20 years. So this, this starts to look like, okay, we're getting somewhere on the energy efficiency side. But the question is, what is the carbon footprint of the building before people start heating it, because the whole result gets elevated if you add the material carbon emissions plus the operating emissions. After 20 years, there's going to be a total here that's dependent on these on the footprint of these materials. And again, from that study, we can see that we could have close to 140 tons of emissions from this 2-story house in Toronto, so that its overall carbon footprint ends up being almost 150 tons after 20 years. And that means that the material carbon emissions from the worst case study house in that study, it takes 315 years of operations to equal the carbon footprint of the materials themselves. So clearly, when we're dealing with materials on this scale, this is where the priority lies, because it's going to take 300 years to make that up with operations. If we use a better range of materials, we get the 20-year carbon footprint of that building down to 40 tons. And now the material carbon emissions are equivalent to 70 odd years of operating emissions. And here, if we start getting into the carbon storing, so in this case, our sort of best conventional model in the Enercan study was just shy of 20 tons of net carbon storage. This finally looks like the kind of thing that I could show my daughter and other young climate activists and say, okay, now I'm doing something for the climate. If I build you this building, it's got 19.7 tons of storage the day I build it. It operates for 20 years very efficiently on clean energy. In 20 years, it's still storing a net of almost 11 tons of emissions. So this starts to be not just, oh, we did a little bit better, we knocked a bit off our emissions. This is, okay, we both made and operated a building over the next few decades that is not contributing to climate change, and in fact, is helping to reverse climate change. And then if you've been following along, so it's going to be net carbon storing for the next 45 years, assuming that our energy source continues to have the same emissions profile. So, that becomes a climate solution type building, and not just we did a little bit less harm. And then, if you've been following along, you'll know that the next example is going to be this best case. And this is why I'm excited to be talking to the Eco Builders Guild, because I believe that these are the kinds of things that if we are putting our minds to it as eco builders, we're the ones setting these examples that show that this is what we can do. And here, after 20 years, we still have almost 75 tons of net storage after building the building and operating it. And so this is how you look Greta Thunberg or my daughter Emma in the eye. Yes, I am doing what I can do to, try to help you have a habitable planet by the time you're ready to inherit it. So this then just looks at the scale of the possible results when we include both materials and operations. So, at the worst case scenario, our building could be contributing almost 200 tons of emissions over the next 20 years. And in the best case scenario, it could be drawing down almost 75 tons. And so it's a conscious choice where we land on this spectrum. All of these things are doable and achievable. There's nothing here that is rocket science or that's relying on technology we haven't yet invented, or materials that don't yet exist, or equipment that we can't buy. All of this is doable now. And so, we as the eco builders, we need to be the ones choosing these projects over here on the far right, and making sure that that's what we're actually doing by knowledgeably accounting for the carbon intensity of all the materials, and being able to document it and tell people, like, this is what I do, and this is why it's important, and sort of really making the case that this is what we currently can do, and where everybody needs to be as quickly as possible. Now, the whole notion of carbon storage in buildings gets a little fraught, especially when people from industries who are sort of threatened by that notion, they really want to draw attention to the fact that, well, yeah, you might be putting a bunch of carbon away, but when the building's lifespan is over, all of that carbon comes back out again. And so maybe it's actually not carbon storing, maybe it's just like carbon neutral. But climate science tells us something different. Climate science tells us that removing a ton of biogenic carbon from the carbon cycle, so if we're taking a material, say like waste paper or cardboard for cellulose insulation, like straw from grain harvesting, like hemp herds from hemp harvesting, if we're taking material that was, first of all, grown, so it absorbed CO2 from the atmosphere as it was growing, so we're not taking carbon out of the earth, we're taking carbon out of the atmosphere. And if that carbon was destined to go back to the atmosphere fairly quickly, if we can interrupt that and put it in a building, that if we put that in a building for 46 years, that's the same as preventing a 1 ton pulse of carbon at the same time. So, 1 ton of carbon emissions over 100 years does what's called 46 ton years of damage to the climate. And so putting 1 ton of carbon out of circulation for 46 years essentially undoes that damage, or is that, the same as reversing that damage. And so, if we're making buildings and putting these materials in buildings that we expect to last sort of between 40 to 50 years, which I would hope that we're all doing, then even if that carbon comes back out of that building, it's a new emission 50 years from now. But the fact that it was put away for 50 years has had the intended impact of negating a ton of emissions. So we would hope that our buildings last longer, and we can certainly be smart about making sure that the carbon that goes into buildings is recycled, reused, turned into biochar. There's a lot of things we can do with that carbon when it finally comes out of the building. But if we can manage to put it away for between 40 to 50 years, that's something really meaningful and something really important that we can be doing. And we can also use this ton-year accounting to account for materials that might not stay in a building for that full length of time. So, if I'm putting a biogenic material in my building, if I put 100 tons of that material in and it's only there for 20 years, then ton-year accounting says that's the same as offsetting 43 tons of emissions. So, about half the value of what you put away. If you do 100 tons for 46 years, it's worth 100 tons. But if you put the same 100 tons in the building and it lasts 80 years, you've actually done the equivalent of offsetting 174 tons. So, the longer we keep that carbon out of the atmosphere, the more its impact sort of continues to manifest. Sorry, I'm not sure why some of these illustrations don't come out. This is a breakdown of the category impacts of different materials in the Nelson and Castlegar study. I will describe it to you. It shows concrete as the biggest impact across all the buildings in the study, insulation as number 2, and cladding and windows pretty closely tied at 3 and 4. And that those 4 categories are the sort of lion's share of the overall emissions from these homes. So with concrete, this is, and I think there have been other sessions already here at the summit about this. We need to be doing a lot better with concrete. If you take a scan of the available EPDs for concrete in North America, I can find the best achievable concrete from a manufacturer at 136 kilograms of emissions per cubic meter, and I can find at least 20% of the EPDs are 650 kilograms or higher. And here in Canada, the concrete industry says that the Canadian average for residential strength concrete is about 370 kilograms per cubic meter. So that means that, if I'm pouring 1,000 square feet of 8-inch thick concrete wall, I can have a carbon footprint of about 2.5 tons or over 12 tons, and it's the exact same wall. It's the same size, it's serving the same function, it has the same strength, but its carbon impact, there's a 10-ton difference just in that one building, by working to identify and source the best concrete that I can. And so, one of the biggest things that you can do with concrete is just talk to your concrete supplier, ask them about their EPDs, and both encourage them to improve their number and go with the supplier that can demonstrate that they have the lowest number in your region. And we can also look forward to some great things coming in terms of biological concrete. Biomason has their BioLith product in the market now in a limited way as both tiles and bricks. And this is a microbe-grown concrete. So they inoculate sand with a microbe and they feed it, and it excretes calcium carbonate that glues the sand together. And so you actually have a net carbon storing tile and brick. Living Materials Lab has an algae-grown concrete that works in the same way, but using algae as the material that pulls down the CO2 and turns it into calcium. And then we also have aggregates that are made from atmospheric carbon. So Blue Planet Systems pulls CO2 out of smokestacks and turns it into limestone aggregate. And OCO takes waste minerals and carbonates them. But in both cases, you sort of have a net carbon storing aggregate that you can put in your concrete, so that potentially, even if we don't fix cement binders, if we can fix the aggregate side, there's a lot more aggregate than concrete aggregate than cement in a concrete mix. And so carbon storing aggregate could start to turn what's currently the worst material in our buildings into one of the best. Insulation is the second most impactful category in the study. And here again, looking at EPDs, if you look at a range of insulations, you'll see that what's pictured here is fiberglass. That amongst the different fiberglass manufacturers, there can be actually a really appreciable difference in the carbon footprint of a material that looks exactly the same. So you can kind of choose lower carbon options from the category you're already using. You can change materials to lower carbon options, or you can change materials to carbon storing options. And residential buildings are great for the amount of insulation to the overall amount of materials in the building, such that carbon storing insulations like cellulose can turn a building from a net emitter into a net storer relatively. And so, yeah, cellulose figures highly in the currently available carbon storing insulation market. Hemp fiber bat, which is now being made in Canada and soon to be made in the US, is another great option. Wood fiber in all its many forms, as board, bat, or loose insulation, is another option. And straw in both its loose and baled form is another great carbon storing option. And I'm sure around these tables, lots of people are familiar with these and also other carbon storing insulations. And also, you might be familiar with people who are now starting to panelize these insulations for the folks that don't want to find, source, or actually install the insulation themselves. Panelized cellulose panels and straw and hempcrete panels are also a great way to be able to incorporate these materials into our buildings. There's also some interesting carbon storing claddings coming down. The corrugated hemp panels are now commercially available in the UK and hopefully here soon. There's a company making a rice hull based cladding that's carbon neutral. The lime cork plaster mixes coming out of Europe are also net carbon storing. Things like heat treated wood, depending on where the wood's coming from, can be net carbon storing. So And again, this is just a sample of the things that are becoming possible in terms of the cladding side. So those are the three big categories: concrete, insulation, and cladding, that you really want to be focusing your efforts on. And I'm just going to wrap up with a few quick case studies. Here is the most recent building we did at Endeavour. It's for our local university, Trent University, their new forensic crime scene classroom. It's a net carbon storing building with about 6.8 tons of net storage. So just a little bit below the zero line, but for a code approved commercial institutional building, it's a pretty great result. And a lot of that carbon storage came from both the hempcrete block system that we used for the walls that you can see in the top left picture, and also a lot of hemp bat and cellulose and wood fiber insulation in that building, and foam glass as the insulation under the slab, which isn't carbon storing, but has a much lower carbon footprint than all the other types of insulation that could be there. So the materials that can't be carbon storing, if you can choose the lowest carbon option, that means that the carbon storage that you're accomplishing sort of goes further to driving the net number to zero or below. And I also just want to point to some examples of larger projects. Here in North America, we are way behind the Europeans in terms of moving these kinds of materials forward. This is a very large prefab hempcrete and mass timber Marks and Spencer store in the UK, a large prefab straw bale university building in Nottingham in the UK, the Jules Ferry residence in France. It's a 35-unit, 7-story apartment building made from mass timber and prefab straw bale wall panels. The Louis Michel School, similarly prefab straw bale panels, making a very large building in an urban setting. So, this is not necessarily, doesn't need to remain in the realm of cute little residential buildings in the woods in North America. This is, we need to be taking our knowledge of these materials to a scale that begins to replace even the larger carbon emitting buildings in our environment. So I'll just wrap up by sort of highlighting that I think as eco-builders, we really need to understand the criteria that we're using to call ourselves eco-builders, and to be able to provide really knowledgeable explanations of what we mean, that we need to design and build to meet as wide a set of those criteria as possible, and actively participate in both scaling up and what I call scaling out. So scaling up includes, helping more of these types of buildings to be made, as well as larger versions, and scaling out being, helping builders, the public, governments, people at all levels to understand that, we all need to be adopting this. And we also need to really concentrate on building what's needed for the people who need it most. A lot of the eco building that I'm aware of in my part of the world, and I'm sure in lots of places, are buildings of choice being done by fairly well-to-do clients. And, I understand that we all need to make a living and to keep building again another day. But I think, really making sure that our buildings are trying to serve the community and the people in the community who most need this type of building, making that a priority. And I started my presentation with this picture. I'm excited about it. I just took the picture last week. This is a colleague of ours, Deirdre McGarren at Strawworks, just finished this really great, about 2,200 square foot health center at a local camp for kids. And I feel like, she got this right on every count. It's it's a net zero building in terms of its materials. It's a net zero building in terms of its operation. It's an electric building, but she didn't just use a heat pump. She used a sand and heat pump so that the refrigerants in the heat pump system are not potential leakage of those isn't a potentially huge driver of climate change itself. She focused on local materials, did a really great low carbon foundation, including, you can see, using some of the limestone slabs that came out from the excavation as footings for those posts. She used earthen floors throughout the building and made a really concerted effort to make sure there were no toxic materials anywhere in the building, including the sort of paints and final finishes, installed a composting toilet system. And, it is at this kids camp, and everything in the building is educational and labeled. And so, also kind of teaches hundreds of kids and the next generation about what's possible. So thank you for taking the time to listen. And I'm going to stop sharing, and we can switch over to Lucas, who I'm assuming is standing by.
Indeed. Thank you. That was absolutely fantastic. I'm always very excited to hear you speak, and very honored to share the stage. So some of the stuff you mentioned towards the end is a perfect segue into the focus of what I'll be talking about today, being resilience side of things in buildings, so that the embodied carbon we try to minimize up front is stored for as long as possible effectively. So,
great. Okay. Well, I will disappear and look forward to seeing what you have to say.
Thank you.
Can you turn your mic off, please?
All right. Well, I can't see you guys, but hopefully you can see this full screen. The argument or conversation I hope to have today is that I think resilience needs to be part of our low carbon building conversation. We keep kind of chipping away at this, right? We added efficiency, we got that right. Now we're getting upfront embodied carbon kind of well understood, in large part thanks to the work that Chris has done, as he explained. I mean, it's some of the work that really inspired me to be so passionate about this subject. The other kind of element of embodied carbon is, once you build the building, how long is the building going to last? How long is that carbon going to be stored? Looking through the participants, I think I've met the majority of you. If not, very nice to meet you. I'm Lucas Johnson. These days, I'm the chief building nerd at Valley Homes. We're based in Phoenix, Arizona. So I'm speaking to you from Tucson. We moved down here a few years ago because my wife took a job as a tenured professor now at the University of Arizona. Science is my passion. Fighting the climate crisis is also my passion. Green building is kind of how I've done it. I like to call that good building these days. Happy father of 2 kids, love the great outdoors. I have a campaigner personality, which means I love to talk about things I care about. And I'm now what we call a calm business convert. So trying to approach these very scary things in a way that doesn't cause us to sacrifice our own minds and bodies, which is something that often happens. And as Chris was saying, this would be so much better if we were in person, because there's that shared catharsis of the work that we do, and celebrating that and sharing the pain of things we've been through on projects. Very hard to capture that part virtually, but it's great to have you all here, because it clearly means that you care. We've been creating a harsh environment, right? I like to say it's our imperative to solve this problem, especially the people joining today who care and have the professional skills to do something about this. It's our imperative to solve this problem. These are my 2 kids, Hazel and Nova. And a lot of what we're doing is well-intentioned, right? I often laugh about like soy-based spray foam, or that's intentionally just has green coloring added to it to make you think it's a green building product. So a lot of what we're doing may not be helping, right? We have many certified buildings out there, but many of them have not delivered holistically. We have massive moisture failures in buildings. It's, water is the destroyer of all things, especially in building materials. And as we move towards higher performance, more efficient buildings, the risk of moisture failure often is increasing. So we need to manage that really well. Upfront embodied carbon. This is from Chris's 3-minute thesis presentation that was a very inspirational thing for me. So a lot of our buildings, as we just heard about, aren't delivering holistically on a carbon impact sense, and further showing moisture failure risk of high carbon impact materials like foam. So if you've seen me talk recently, you know I always talk about the 5 factors of good building, and good building is the way I like to frame the conversation around how we can build appropriately for the future of humanity. It has these factors that focus on everything from comfort and health to efficiency and renewables, durability and resiliency, which is what we're going to focus on today, social justice, and life cycle carbon impact are also a big part of it, clearly. And they're all tied together too. They're all very interrelated. The big picture right now is a little scary. It's kind of looking like humanity is going to have a rough future unless we take a really radical action in regards to social justice in the built environment. And this is a saying I came up with. Embodied carbon isn't just upfront, right? It's not just upfront materials, but it's also a double entendre, as in it's not socially just upfront either, right? A lot of the materials are coming from extractive capitalistic models that are tearing resources from communities that aren't being properly compensated and are being hurt by that process. And then on the other side of things, workers are having their lives risked to install these high carbon impact, high toxicity products. We're not going to spend a lot of time on that today. There's plenty of other conversations. I have a whole presentation called On Embodied Injustice of Building Products. So if you're interested more on that subject, it's a very important conversation to have. We can talk about it in the Q&A as well if people are interested. So looking again at the life cycle carbon impact picture, one of the sayings I've come up with is if efficiency is king, then embodied carbon is queen, right? Where does embodied carbon happen? Well, pretty much everywhere other than that red circle. Chris was spending time earlier and shared great detail and a great perspective, the best I've seen yet, especially for the residential scale that most of us work at, on the upfront carbon side of things. But a thing that he alluded to multiple times in his presentation is the end of life cycle carbon impact. How long can we get this carbon we've stored through very intentional choices up front? How long can we get that to last in the building? I didn't mention earlier, I should have on the introductory slide, I'm on the board now for the organization, for the Eco Building Guild. And one of the things we like to look at is a 200+ year perspective of building. So 46 years is a wonderful amount of time, but I think we can do a lot better than that if we understand how to build resilient buildings. We can have buildings last for 200+ years, right? Okay, so the scary big picture side of things is that fires, storms, and temperature records seem to be something we need to expect a lot more often. These quote unquote 100-year events are seemingly becoming an annual event, right? That's not good. It's a little scary here. So we need to learn how to do things like building for fire resistance. These are all subjects that deserve a 2 to 4 hour presentation of their own. We're going to cover them very briefly to make sure that we have a good perspective across the board of the key factors to look at, and then we can dig into more details. You're also, most of you, I think, joining from the names I've seen are all looking for 501 level content and get these concepts in general. So to give an example, this is a passive house project. A few of you have probably heard me talk about this before. This was built in Monterey, California area, up in the mountains, very high fire risk area. It was built to be as low carbon upfront as possible with the Gutex wood fiber insulation, cellulose, and Proclima and stuff to protect it all. The goal was to minimize carbon impact, but they were very concerned about fire risk. So the question is, can these very low carbon or carbon storing insulation materials, can they do well in a high fire risk environment? As a building scientist, one of the big challenges we have is you don't often get to do real world experiments on buildings. A lot of what we're doing is research in a lab and trying to apply that to real world, but there's gaps in knowledge that occur there. This, unfortunately, was a chance to try out this hypothesis in reality, because there was a massive fire, being California summers, and things burned down. The entire neighborhood burnt to the ground, but they had followed some rules for fire safety. which is durable passive house levels of airtightness or better. There's a lot of complex science behind why this works, but effectively, airtightness is about, basically creating a barrier between pressure differences. So you can't have air move from a hotter area to a colder area, right? So when there's a fire, you have hyperheated air outside. So there's an even greater chance of that air moving from inside to outside. If you have a durable passive house air barrier that's then protected by high thermal mass insulation, which is also protected by ember-proof cladding and roofing, that system can maintain its integrity in a fire, and you can have a building survive a fire. Is this a guarantee? No, there's no such thing as fireproof. That's a pretty ridiculous, that's a marketing term, not a science term, but you can make buildings highly fire resistant with proper design. Obviously, you need to make the site fire resistant as well, but that's a whole other conversation. So also you want to include continuous fresh air from controlled sources. Unfortunately, we're a ways away from any residential scale ventilation system that can really operate safely during a fire. There are systems that'll help, that can work, but you're going to wreck your filters, et cetera, et cetera. Fire creates some of the nastiest air that you would need to filter. Another interesting thing is for buildings to be deemed as safe for firefighters to enter, we're very rapidly moving towards code in a lot of states where they won't allow firefighters to enter buildings with natural gas or foam insulation because it's too risky for the firefighter. So some pretty interesting stuff there. Showing what happened, this is the passive house after the fire, right? And what happened is there was a durable air barrier that was placed on the sheathing. That air barrier was covered in the high thermal mass insulation, which was then protected by the ember-proof cladding and roofing you see. With that combination, the pressure difference wasn't able to be established to bring the hyperheated air into the building and cause combustion, right? And the ember-proof cladding prevented sparking of exteriors, which are the two main things that lead to fires. Again, too much complex science to really go into detail with the time we have today, but this is a basic thing. We need to design for fire safety. We also need to build to flow with water. I chose this batten photo for two reasons. One is because there's a lot of debate around horizontal battens and do they actually work. Vertical is far better as far as allowing the pressure difference to flow directly. This building is in Phoenix, Arizona. So in that zone, with the way the battens are laid out, the building, we have moisture sensors in the building and it's operating just fine in that cavity. But effectively learning how water moves in your local climate and how to maximize drying and minimize wetting for your climate is a critical part of design. And unfortunately, one of my sayings after doing a lot of modeling for a long time is models are often the best way to justify bad decisions. They can be a great way to look at, does this make sense in general? Is this crazy? But if you're kind of have an agenda of making a certain assembly system work out, you can definitely adjust variables in models because reality is complex and these models look at many, many different factors that all are interrelated. And it's hard to properly value things like thermal diffusivity and wind washing and thermal bridging of fasteners and individual microclimates and durability of materials and occupant behavior, installation defaults, et cetera, et cetera, et cetera. All that stuff's very hard to properly value. So models can start a conversation, but they should never be the end of a conversation. And this will be the one slide I use to summarize this. All leaks are not created equal. Effectively, as we increase air tightness in buildings and increase the amount of insulation, we're making what were big direct leaks out of buildings that actually help with drying and generally into long, slow leaks that can leave a lot of moisture behind and not create sufficient drying. So we have to acknowledge that as we tune up buildings' performance, we're also very much tuning up the dial on moisture failure risk. So key findings to share about how to minimize that. There are many unreliable air barriers and vapor control layers. Basically anything non-continuous, foams, drywall, caulking, microporous membranes, anything that's not continuous is gonna probably not work out as well as you think in regards to both air tightness and moisture control. Air transported moisture is the second leading cause of building failure, meaning the hot, humid air inside buildings gets pushed into enclosure systems, finds cold stuff, condenses, and causes issues. So learning how to manage that appropriately for your climate zone is incredibly important. And some basic rules about minimizing failure risk and maximizing performance. Inboard and outboard air tightness is usually optimal to have both. Not necessary always, but a lot of times that's the case. Vapor permeable insulation is mission critical. You do not want your insulation to act as a vapor barrier. And balanced heat recovery ventilation is mission critical, especially as we continue to improve performance. But even now with current code, a very important thing. We also need to build for comfort, right? Because if buildings are uncomfortable, people are going to leave them and they'll probably get torn down or remodeled or whatever. And there's a huge risk that that embodied carbon that was stored is now negated. So this is a look at what's called thermal diffusivity. It can be thought of as thermal lag in buildings. It's a very important thing to understand, especially in hot mixed climate zones. But cold mixed climates, especially with climate change creating warmer summers, like we all experienced in the Northwest this summer, these things are mission critical to understand as well, right? So I like to call this building science nerd time. We're going to talk about thermal diffusivity. This is me and our lead carpenter, Rigo, applying some materials on a, hopefully very low carbon building up front. Retroactively, I need to go run the beam calculator on this actually. We don't need to go into all these details of what this is right now, but effectively, we're used to looking at thermal conductivity, K, but what we are including now is specific heat capacity, which is how much energy it takes to change the temperature of a given material. For instance, foam takes very little energy to change its temperature of the material itself, whereas wood takes a ton of energy. Think it's a cold night, there's a stump that's been in the sun for a while. The surface of the stump might still be cold after hours in the sun. And if you go deep in the stump, it's going to be cold all day, right? Wood takes a lot of energy to change temperature. So these are things we need to look at. And then how dense is the material, because that is the other factor that you need to look at. So effectively what this can create is when there's a huge, on the top graph, we're looking at outdoor temperature, and the bottom graph, we're looking at indoor temperature. When there's a huge swing in outdoor temperature, what it can cause is a very little swing in indoor temperature, but that little swing is also happening way late at night. So it actually might be beneficial that the heat is then being released into the building. Think about it like hot summer, cold night, right? This time of year in Arizona, that's what we deal with every day. It gets warm during the day, but really cold at night. So high thermal or insulation with good thermal diffusivity properties is extremely beneficial here. To verify this, I did a little backyard experiment. On the left is a wood fiber insulation box made out of Gutex. It's 1.5 inches thick, so it's rated about R5.7. On the right, we have a 2-inch XPS foam box, so it's rated at R10. In theory, R10 should work a lot better, right? Put some sensor push sensors inside of these and left these in my backyard for a year with as equivalent exposure as possible. And effectively, inside the Gutex box, we had a temperature distribution going from about 53 to about 90. So pretty reasonable temperature inside. Inside the XPS box, which again is supposed to be double the R value, we had a temperature range that went lower and much higher, right? It could be fatally high temperature. And if you see the humidity distribution inside there, sneaking in on the bottom there, that's even scarier. Summarizing it in a different chart, the blue is the Gutex and the red is the XPS. This is a daily cycle of it heating and cooling. You can see that at about half the R value, it's providing about twice the performance in this climate. So another thing we need to do is build for community, right? We need to start looking at not just our house, but what is our home connected to? What impact does our home have on our neighbors and the community around us? And how can we share better building or good building with as many people as possible so we can all participate in that community? So I like to say resilience must reach beyond the building enclosure to include the people and the health of their social networks. The question to ask is, how do we connect our homes to good energy and ourselves to good community, right? Not building buildings that isolate ourselves from our community, but that connect ourselves to our community. We have to demand good building, right? This is our house in Tucson. I include this to mention that our house here is on the low end of good building. Certainly not high performance, but it's relatively comfortable, pretty healthy, near zero carbon impact with the solar, including charging our electric car. And we did it for very little out of pocket because we're not wealthy people. You know, we wanted to participate in better building too. So it's not necessarily about high performance versus low performance. Good building is more fundamental. Just like Top Chefs, we can solve many problems by requiring good ingredients as the basis of our work. There's no magical formula that turns bad building materials into a good building somehow. Bad materials create bad buildings. Simple as that. Good buildings need good materials. Good materials need to be resilient. They need to be put into resilient systems, and they need to create comfort. They need to be fire resistant. They need to be water resistant. Zach Semke, as we all I think know, had this tweet after Chris Magwood had actually presented, so little full circle shout out about passive house levels of airtightness, clean energy, and carbon storing materials equals good buildings. I think that's a great way to put it. This photo is me installing some carbon storing insulation. Even though I'm a building scientist, I love playing with tools, and I'll do whatever it takes to get this stuff done. And a big shout out to a fellow presenter and all the work that's being done by him and a huge group of colleagues, Builders for Climate Action. If you care about this stuff, this is the resource to dig into. And just want to say thank you so much for the time today. And that's the end of my show here.
Fantastic. Thank you, Lucas and Chris. That was, just always really great to hear and see the data that you guys are collecting and the information that's available now. It's continues to grow. It's very exciting. There was definitely a lot of questions that were coming up during the chat and some comments. One of the questions was around the algae concrete and like how long that takes and to make. And I was also thinking about like space. Sometimes people talk about how organic foods and veggies take more space to grow and rotate those crops. Like, is there more space required and more other things required for the algae concrete, and how long it takes?
I would say that's a material that I know the least about of everything that I touched on. I've worked on a couple of papers with Will Schrubar, whose lab is one of the labs that's doing that. I think how much space it takes up. We also have to think, well, what it's replacing is concrete. The space concrete takes up is excavating all of that limestone and gravel to be the concrete. So we might not see that, but moved around the world to make concrete as we know it now. The photos I've seen of the process, they're not producing it commercially right now. It's essentially little form swimming pools with seawater and algae in it, being given sunlight and air. So I guess just like anything that's being formed, you need as much area as it takes to form that. But can certainly imagine, like the folks that are making mycelium insulation now, that happens sort of in a stacked format and indoors, and sort of with a regular cycling through that growth period. So I think all of those grown systems, they make more sense, like because they're not extractive. You can actually benefit from having micro producers in lots of areas instead of one macro producer doing it centrally and like hauling raw materials in and shipping product out. I think a sort of version of the mycelium, algae, and other sort of grown building materials looks a lot more like every city has, small warehouses where this stuff is being grown for the local market.
Absolutely agreed. And it's interesting. It's been a while since I did this research, but a decade ago, I was retained by the federal government, of all things. I can't actually talk about exactly too much on this. It's a kind of weird story in my life. It was a little side consulting contract, but what we looked into is algae-based biofuels. And effectively, the results are algae are an extremely finicky organism in that they can get invaded by other algae species very easily, and you can lose the algae species that you're trying to grow, et cetera, et cetera. The type of algae that are used for fuel are the most sensitive, difficult type to grow, so that's why that didn't really work out overall, I would argue. Interestingly, with what Chris is saying, the type of algae that you would use for an aggregate material would be a lot easier to grow, and certainly could be done in a much more distributed system. I mean, it could almost be like, if you had the way to process it, you could almost just set up a pool on your job site, grow the algae, and probably get a bench worth out of that. But I'm saying you can get it to a pretty micro distributed level, and it can go pretty quickly. Algae is a very fast growing organism.
And same with the mycelium. Like, we did a project where we grew the mycelium insulation on our straw bale wall panels in situ. It's a 3-day grow. So, we put it down, we gave it some flour, some water, covered it up, and uncovered it in 3 days and dried it out. And we had grown 1.5 inches of exterior insulation, right on the job site. So, yeah, I think there's that part of all of this is so exciting. And these are the materials that aren't commercially available now. As I scan the Q&A, it's like, well, how much does this cost? And it's like, well, I can't even give you a cost for algae bricks because nobody's making them at any kind of scale, but it doesn't take much. And if we figured out how to blow bubbles in petroleum and turn it into an affordable insulation, things that grow on their own steam with a very small bit of food and water should be a lot cheaper than most of what we're used to working with.
Yeah, no, I'm so glad you bring that point up, because in my mind, there's so often this conflict between high-tech manufacturing and all the progress we've made there, and the bad materials that are typically outputted right now from that process. It doesn't have to be that way. We can put good natural materials into a high-tech process and create good materials, usually in a much easier process overall than, I think, as I've heard you say before. It's so crazy when we think about, say, fireproofing, and people are like, well, I think I'll use that fire-resistant foam insulation for my building. That, basically napalm, stabilized napalm seems like a really good thing to put on my building because, it passed some lab tests. It's so interesting how we get so confused about the overall impact of these decisions we're making, and we get worried about stuff that's perceived as site grown. That could be very much perceived as some like hippy dippy insulation from a conventional building sense. But if that was made in some factory down the street, they'd be like, wow, this is an amazing product. The psychology of that side of things is fascinating to me.
Yeah, a really good friend and colleague who's a straw bale builder locally here gave a great presentation a couple of years ago where she kind of took the 3 things that people with straw bale. It rots, it burns, and it's too expensive. And she actually went through like the hundreds of documented buildings that there are in this province that are made that way, and found no examples of fire being a problem. She found many examples of straw bale buildings that had fires where the straw wall component was the thing that survived the best out of the rest of the building, and found no big problems with moisture. But she found a number of houses where there had been roof leaks, plumbing leaks, like water issues, where the straw was the thing that dried out and lasted, and other materials affected by those water leaks weren't. And she was like, everybody thinks that these are the problems, and these are actually the things that this material is fabulous at handling. And so, yeah, I think there's just so much around the perception that, we just assume, oh, that stuff's going to rot, burn, or, something. And the one that we get off the store shelves isn't. And I think, there's so much proof out there that that's, not the case on either side necessarily.
Yeah, my 3-word quip about it is marketing trumps science.
Absolutely. So, Chris, on that note about the straw bale, is there moisture concerns with using it for walls, or what kind of special design considerations are there?
Sure. I mean, there's the exact same moisture concerns that are the moisture concerns that we all deal with in any kind of building. So, we want to stop gross water leakage into components that have straw, just like we want to stop gross water leakage into any kind of building material. We want to make sure that water that gets in there has the ability to dry out. And we want to make sure that, that the material is being given the best possible chance to A, stay away from water, and then B, survive exposure to water. And like I said, straw has shown itself to be really quite resilient that way. If you think about straw, like a piece of straw is just a little tree. I mean, if you look at the actual makeup of it in a microscope, it's pretty much the same cellulose that a tree is made out of. And so if you think your buildings that have, say, wood framing in them are being built in a way that they will survive long-term, the way that moisture, they may be exposed to moisture, then putting straw insulation inside that wood framing should give you no extra reason for concern, because they respond to moisture in exactly the same way. And if you're confident you can work with wood, then you should be pretty confident that you could work with straw or hemp or sugarcane bagasse or any number of ag fiber materials. All of that cellulose reacts the same as wood.
And they're a more similar material, and where we get into issues is when we have different material profiles in the building, right? Like foam blocks moisture transfer, and that causes issues because it makes the moisture build up where it can, which is the wood, right? Going back to the question about straw bale, going to those core principles I was talking about, because I think we always just need to go back to core principles. Building science tends to overcomplicate things. It's like, I want to use this product, let's figure out a way to do it. And it's like, but you're just defying a core principle of construction. Let's not do that, is often the better approach. Straw, people are worried about that, but it doesn't defy these core principles. From a fire standpoint, it is high thermal mass insulation with a durable air barrier, protected. That's ember-proof cladding. The air barrier and the cladding happen to be one in this case because they're the stucco, usually a lime plaster stucco, that's put onto these buildings, and that's also vapor permeable air tightness throughout the enclosure. So it meets the core principles of good building. Whereas, and then the funny part is people are bringing a building with, like, say, microporous membranes and foam insulation to the table because they've seen that all the time, and they're like, oh, well, this is the safe, normal thing to do. You're like, no, that defies like 6 core principles. It's weird where we start the conversation often as conventional's good and this other stuff's experimental. It's actually that conventional is experimental BS that we're driven to doing by marketing. When we know how to do better building, we just get marketed to do something cheaper.
There was another question about composting toilet systems and how you get to use those in buildings or homes, and what kind of challenges you have with jurisdictions on those.
We don't get to install them as often as I would like to. That's one of the last sort of remaining lines in the sand from a client point of view. People who will consider interesting materials, consider interesting mechanical systems, will kind of like go out on on the alternative side on all kinds of things. We'll draw the line at composting toilets. So, we don't get a lot of opportunities, but where we do, there are some really great systems out there. And I mean, I'm in a particular code district, but here in Ontario, there's about a dozen code approved, CSA approved compost toilet systems that are considered accepted solutions in the building code. So not every composting toilet is, but most of the good ones that I would want to install have their code approvals for my jurisdiction, and I'm assuming the same would be true in other places. The biggest problem with them is the really good systems and the ones that are code approved. I noticed there was a thing about cost in there, and really most of the things that we're talking about here don't cost more. I can build that low carbon storing building pretty much the same cost as anybody can build any building. But a good composting toilet system is like $10,000–$15,000, and there's kind of no way around that. And when you compare that to, especially if you're in a city, the cost of sticking a $200 toilet on and sending everything to the sewer, there's a $14,000 difference there. And so it is one of the areas where somebody is paying a lot more to sort of make that choice. And so if the sort of ick factor of having a composting toilet isn't what stops people, then it's often the cost. So that's been our experience.
Less expensive solutions for like single family residents, like a backyard cottage or something like that, isn't there? I mean,
well,
like
the best composting toilet in my mind is the simple bucket toilet, and that's an almost zero cost, and it works really, really well. It's not code approved, and most people don't want it, even though it's shockingly clean and odor free, more so than most flush toilets. But if you either don't want to or can't do that sort of $100 toilet, the next thing that works really is a remote chamber composter. And the people who I know who've had really bad experiences with the composting toilets, they've bought the sort of middle of the road, all in one sort of little plastic throne type units. They're a disaster. They don't have enough capacity to store material and have it actually compost in the unit, but it's too big and messy and hard to take out compared to a bucket. And so I've heard only bad things from people who use those, and I've taken those out of a number of buildings for people. So I think it is a case where that, like, you kind of get what you pay for, and getting a cheap composting toilet is in all likelihood not going to make you won't enjoy the experience.
Got it. Lucas, Ian was asking about the low embodied energy cladding product that's fireproof.
Oh, I mean, there's a few options. I'd be really interested to hear more about the cork plaster. Is that one of the things you mentioned, Chris?
A couple of companies that make a lime plaster where the aggregate is cork instead of sand, and so it's lightweight, insulative, and the cork is sort of doing the carbon storing. So, I mean, that would be a highly fire resistant cladding. Fiber cement is sort of a go-to. It's not that low carbon, but if the rest of your building is good and you need a really fire durable exterior, that's a good choice. Heated wood and or charred wood can also be a good. Earthen plasters are a great choice for both low carbon and fire resistance. I'm trying to think,
yeah, so like, Kebeni, Akoya, those can be decent.
Yeah.
Any sort of Shoshigibon can be decent. It was because of some work I was doing in California, and some of the slides I drew this presentation from. Basically, the passive house I helped work that survived the fire has led me into this whole fire science community of people that on the West Coast, and I've been getting to learn a lot from them, and it's been fascinating. One of the key things that comes up time and time again, first and foremost, is site protection. You cannot have fire coming up against your building. Again, there's nothing that's fire proof. There's highly fire resistant. So if you have a bunch of embers hitting things, building materials can deal with that. If you have a direct flame source on something, building materials are not going to do that. So you can't be stacking combustible stuff around your building. You need to be keeping proper clearance of combustible landscapes, blah, blah, blah. There's a ton to it. once you've done that, then stuff like Akoya, Thermocork, et cetera, will probably be just fine. There are also some really interesting intumescent, being fire-resistant paints that are coming onto market, which could revolutionize things, but those are a ways out from really being commercially viable.
Chris and Lucas, we have about a minute left. Once we get out of speaker mode, there is a table that we'll see in the bottom right that I invite both of you to go down to, and anybody who'd like to have further discussions with these two on their presentations. If you have any more questions, that would be great. And then we can free up this platform for the next presentation in about half an hour. I don't know if there's anything we want to wrap up with here in the short term.
Chris, do you have any closing words?
No, just, I'm glad to have been able to do this today, and really appreciate people's sort of time and listening in, and the great questions that we got. Yeah,
I would like to thank both of you as well. This a great presentation, really informative.
I would second that. It's great to be part of this. I've usually been more involved with this event in past years, but this was like capturing all of my joy in one little hour-and-a-half session. So thank you.